As discussed in the first video lecture on charge carrier excitation, this week we will focus on the behavior of the charge carrier's electron and holes in a semiconductor. We will use the semiconductor material silicon as an example. And again, will make a drastic simplification. The silicon network is a three-dimensional network. The blue spheres represent the silicon atoms, and the red dot represent the valence electrons in the valence band forming the bonds with neighboring atoms. To illustrate the behavior of charge carriers in a silicon lattice, I will flatten the material and consider the silicon lattice to be a two-dimensional squared lattice. In this two-dimensional network, every silicon atom has 4 bonds with its neighboring silicon atom, like it has a three-dimensional network. In this schematic silicon network, we put some charge carriers. The animation shows the mobile electron, which again are indicated with the red dots. Secondly, we show the holes, which are in this illustration indicated by the black lined dots. They are part of a molecular bond in which one of the two valence electrons is missing. Both electrons and holes can move freely around. So far, we discussed that we can manipulate the density of the free charge carriers using temperature. The higher the temperature, the more free electrons and free holes can be excited. Another approach to increase the charge carrier density is using doping. Up to now, we have considered pure semiconductor materials without any impurities. These semiconductor materials are called intrinsic. It means that the density of electrons and holes are the same in the material. We can intentionally incorporate impurities in the material. This is called doping. Doping can have a significant effect on the charge carrier density, which I will explain now. As example, we take again silicon. Silicon is a material which has 4 valence electrons. In the periodic system, silicon is part of the column with atoms having only 4 valence electrons. At the left side of the 4 valence electron column, we see that we have materials with only 3 valence electrons, like boron, aluminium, and gallium. On the right side of silicon, in the periodic table, we have atoms which have 5 valence electrons, like nitrogen and phosphorus. First, we are going to intentionally put phosphorus impurities in the silicon network. Phosphorus has 5 valence electrons. The phosphorus atom will make molecular bond with its 4 neighboring silicon atoms. Since the phosphorus atom has 5 valence electrons, it has 1 electron left over. This extra electron is easily excited to a free mobile state. The phosphorus atom left behind is not neutral anymore and becomes a positively charged entity. This positive charge is fixed to the position where the phosphorus atom is residing in the lattice. The result is that by adding an impurity, we have 1 extra free mobile electron available and a fixed positive charge in the background. This is called n-doping. For n-doped semiconductors, the electrons are called the majority charge carriers, as the density of electrons is much higher than that of the holes. The holes are called the minority charge carriers in an n-doped semiconductor. N-doping of silicon can also be illustrated by an electronic band diagram. The phosphorus atoms are represented as donor states. These donor states have an energy level within the forbidden band gap of the silicon matrix, which can be occupied by electrons. The energy level of the donor state is closer to the conduction band than to the valence band. This means it requires much less energy for an electron to jump from the donor state to the conduction band than for an electron from the valence band to the conduction band. At typical room temperatures, many to all of the electrons in the donor states can be excited to the conduction band. As a result, we have more free mobile electrons than mobile holes in an n-type semiconductor. The electrons are the majority charge carriers and the holes are the minority charge carriers. Secondly, we are going to intentionally put boron impurities in the silicon network. Since boron atom has only 3 valence electrons, it is missing 1 electron to make a molecular bond with its 4 neighboring silicon atoms. As a consequence, 1 molecular bond is filled with only 1 electron. This entity is the same as the hole. This extra hole is easily excited to a free mobile state. The boron atom left behind is not neutral anymore, but becomes negatively charged. This negative charge is fixed to the position where the boron atom is residing in the lattice. The result is that adding a boron impurity, we have 1 extra free mobile hole available and 1 fixed negative charge. This is called p-doping. For p-doped semiconductors, the electrons are called the minority charge carriers, as the density of electrons is much smaller than the density of the holes. The holes are the majority charge carrier in p-doped materials. P-doping of silicon can be illustrated by an electronic band diagram as well. The boron atoms results into acceptor states. These acceptor states have an energy level within the forbidden band gap of the silicon matrix, and the acceptor states can be occupied by electrons. The energy level of the acceptor states is closer to the valence band than to the conduction band. This means that it requires much less energy for an electron to jump from the valence band to the acceptor state than to the conduction band. For silicon at room temperature, many electrons of the valence band can be excited to the acceptor states. As a result, we have more free mobile holes than mobile electrons in a p-type semiconductor. The electrons are the minority charge carriers, the holes are the majority charge carriers. You have been introduced how the concept of doping can be used to increase the density of the majority charge carriers or decrease the density of the minority charge carriers. In the next video, you will get a feeling on the typical concentrations of majority and minority charge carriers in silicon and how this compares to charge carrier generation due to light absorption. So see you back in the next video.